to the proof. So the proof essentially is that you start with HP acting on a phi. Now remember there are two particles, I'm not writing 1, 2 every time explicitly. So HP acting on an arbitrary function. Please remember, if I have to prove that they are identical, I must allow left and right hand side to act on an arbitrary function and then show they are equal. Right? Then only the two operators. Operator equality is a strict equality. So if I do this, what does P phi does? It will give you H of 1, 2, phi of 2, 1. Correct? This was originally phi of 1, 2. Everything had 1, 2 originally. But now, because P is acting on phi, and I am giving you the definition of P, permutation operator, it simply interchanges 1, 2 to 2, 1. So I get H of 1, 2, phi of 2, 1. Let me do it in the reverse manner. P 1, 2, H 1, 2, phi 1, 2. Now, look at P. What is it acting on? It is actually acting on this composite thing. Not just phi of 1, but it is acting on whatever is H phi. So what is it going to do? It is going to interchange 1 to 2 and 2 to 1 in the entire function. So what do I get? I get P of 1, 2, H 2, 1, phi 2, 1. Right? I just... Huh?
The P12 has to be.
Oh, sorry.
Because you just acted operator. The next one. In the next
So
there P will remain. The next one.
So this one. So the P12 simply changes the makes it H of 2, 1, phi of 2, 1, which you can see is identical to this. Because H of 2, 1 is nothing but H of 1, 2. So I must complete this proof. Because of the fact that the quantum Hamiltonians, I can interchange the coordinates, H of 1, 2 and H of 2, 1. I can now apply that and show that the H and P commute. This is a very fundamental thing, just like I show in harmonic oscillator, where the potential is an even function, I can show that the Hamiltonian commutes the parity operator. And from there I argue that the parity operator eigenfunctions are odd or even, hence the harmonic oscillator eigenfunctions are also odd or even. So I'm going to come to exactly that same theorem. Now that I know that the Hamiltonian commutes with permutation operator, my eigenfunctions of Hamiltonian must also be eigenfunctions of the parity operator, permutation operator. Please remember the very important theorem in quantum mechanics that if A and B commute, they have simultaneous eigenfunctions. Of course, only eigenfunctions, not eigenvalues. So I'm going to recall that theorem and then say that my eigenfunction of the Hamiltonian is going to be an eigenfunction of the permutation operator. So the eigenfunction of the Hamiltonian can be more difficult to obtain. So let me now find the permutation operator eigenfunction. So that is very easy to do. So what I do is that I go to the permutation operator eigenfunctions and let us see its property. So I write P of 1, 2 of psi of 1, 2 as some lambda times psi of 1. So that's my eigenvalue equation for the permutation operator. I square it. So essentially I allow P12 to act twice. So I have P12, P12, psi of 1, 2. And quite clearly, by the eigenvalue equation, this will be nothing but lambda square psi of 1. I hope that's clear to all the students, because this first gives you lambda psi 1, 2. P12 again acts on psi 1, 2 to give you another time lambda psi 1, 2. So you get lambda square psi 1. If you now allow the definition to act, what do you get on the left hand side? You have psi of 2, 1. This acts again to bring psi of 1, 2. So you have eventually an equation which is psi of 1, 2 equal to lambda square psi of 1. Which means lambda square is 1, lambda equal to plus minus 1. It's a very important result, and exactly the same way the proof for the parity operator goes. So lambda equal to plus minus 1 essentially means that this eigenvalue of the permutation operator is either plus or minus 1. So I can now replace this as plus or minus 1 and write this equation as P of 1, 2, psi of 1, 2 is plus or minus psi of 1. And then I reapply the definition again on the left hand side, and then I get psi of 2, 1 equal to plus minus psi of 1. It's a very brilliant proof actually. And this can be done for many symmetries. In fact, this is one of the first example of group theory. Although it is never taught in group theory, but this is actually an example of group theory, how this symmetry. Because remember, all operators which commute with Hamiltonian are called symmetry operators. So when chemists talk of groups and all that, these are all operations which are commuting with that Hamiltonian, by definition. So permutation operator is actually a symmetry operator for many electron Hamiltonian. A trivial, so we don't always worry because already the exclusion principles are known. But it is important to realize that if I interchange the coordinates of the two electrons, they must be plus or minus. But when I say coordinates, now I have to be careful. I have to interchange everything. So spin, space, everything. So that is important because spin now must be brought together. If this is plus, of course you all know these are called bosonic systems. And for the minus, these are called Fermi systems. So the electrons follow minus, and this is why the antisymmetry comes in. So once the antisymmetry comes in, Pauli principle follows. So I always say Pauli exclusion principle is not more fundamental than the antisymmetry. The fundamental principle is antisymmetry. Pauli exclusion principle is a corollary to that, and I will show you that very soon. So let's say I take a helium atom now. So helium atom, so if you agree that all wave functions for the electrons are antisymmetric, and this is what we are going to worry about. So these are all antisymmetric wave functions. So for the helium atom, I have so-called 1s orbital, and I have 2 electrons. So I have various ways of filling them up. I can fill them up like this, and this is my 2s. I can fill it like this, right, 1s, for the ground state. Of course, I can excite an electron to 2s. I get several interesting properties which I will come later. What happens in the excited state? But assuming that the spin pairing is much lower in energy than the 1s, 2s, I have these 2 options of filling up. Clearly, you will find that this violates antisymmetry. This wave function violates antisymmetry because I cannot construct a function with 1 electron in 1s alpha, another electron in 1s alpha, which can be antisymmetric. There is no way I can violate it. It is obviously clearly a symmetric function. So it could be okay for Bose particles, but not for electrons. So I can't do it. On the other hand, if I write for this, it will be clear that I can do it. How? So if I write this function, it will be 1s alpha 1, 1s beta 2. So if I just stop here, of course it doesn't look like there is any symmetry or antisymmetry, right? It has no symmetry actually. But interestingly, I can just interchange the coordinates of electron. I can say that 1s alpha has 2, 1s beta has 1, and just make a subtract these 2 parts, and then you can quite clearly see that this is an antisymmetric function. So you have, if I now interchange 1 and 2, this will become 1s alpha 2, 1s beta 1, but with a plus sign. This is going to become this with a minus sign. So the overall sign will change. So what is important is that it was not possible to construct any function which is antisymmetric with this configuration. Whereas it is possible with 1s alpha and 1s beta, and hence, of course, the Pauli principle is a corollary to the antisymmetry. So please understand, the antisymmetry is more fundamental because antisymmetry comes from the nature of the Hamiltonian. The Hamiltonian is identical particle Hamiltonian. Hence, if I interchange 2 coordinates, they are same. And because of that, it commutes with the permutation operator. Permutation operator eigenfunctions are either symmetric or antisymmetric. So let's take the antisymmetric part, which is for fermions, and that actually experiments better. It is very hard to theoretically show which is boson, which is fermion, but the negative one is fermion. Then of course the wave function must be antisymmetric. And then we find that I can't construct, and hence the Pauli principle. But so that is the reason Pauli principle comes later. And the interesting part, of course, happens when I go to an excited state atom. And they are, of course, much more interesting. Because now I can have an alpha-alpha. If I put 1 electron here, and I can actually construct several different possibilities. We'll come to that later in the talk when I go to the electron correlation slowly. What is important is that if you look at this function, this can be first normalized, and for normalization I need a 1 by square root 2. Now that is a trivial part. I write this as 1s alpha. Okay, so this is a simple way of writing, showing that the first is always 1, second is 2, 1, 2. Okay, so that's a simple way of writing. What is important here is that this can be written as a Slater determinant by putting 1s alpha 1, 1s alpha 2, 1s beta 1, 1s beta 2. So this can be converted into a Slater determinant. If I expand this Slater determinant, of course, with a 1 by square root 2 factor, you will exactly get this. So Slater determinants are a way of writing this, and they are much more easy because the Slater determinant, because of the fact that determinant, you can easily see that if I interchange 1 and 2, it is always going to be antisymmetric. So please look at the determinant very carefully. The rows and columns can be interchanged incidentally. I have put first row 1 orbital, 1s alpha. I have 2 orbitals, 1s alpha, 1s beta. And then second row is 1s beta. Then I have put in one column coordinates of 1, another column coordinates of 2. So you have to be consistent. It doesn't matter, you can change it, row and column, but you have to be only consistent. And then you can easily see that interchanging 2 electrons is nothing but interchanging 2 columns. And if you write the other way around, it is interchanging 2 rows. Since it's a determinant, it changes sign. So determinant becomes a very handy way of writing. For 2 electrons, I could actually construct this by inspection. If it is many electrons, it will be very hard for me to construct. Like nitrogen atom. I give you 1s squared, 2s squared, 2p3. Very hard to construct an antisymmetric wave function by inspection. So then what I do, I simply write a 7 by 7 determinant for nitrogen. So if I have to write it, let's say I do it for now a little larger atom first, let's say lithium. So I assume that it is 1s alpha square, 1s squared, which means 1s alpha, 1s beta, 2s alpha. Then I simply construct a 3 by 3 determinant. So first row is 1s alpha, second is 1s beta, third is 2s alpha. And then this is a column, 1, 1, 1, and similarly write the second and the third column. So 1s alpha 2, 1s beta 2, 2s alpha 2, 1s alpha 3, 1s beta 3, 2s alpha 3. So if I write these 3 rows and 3 columns, it is automatically antisymmetric. As you can see, I don't have to worry about it, because any interchange assumes, any interchange automatically guarantees that the determinant would change sign. So that's a beautiful idea that the John Slater actually gave, and these are called Slater determinant. And later on I'm going to use these determinants. So Slater determinants have the right symmetry. Once I know what are the orbitals, Slater determinants guarantee Pauli exclusion principle. So that's the beauty about this description, and all many electron functions, however I want to write, will always be written in terms of Slater, because each determinant automatically guarantees the antisymmetry. A combination of determinants will also automatically guarantee antisymmetry. So I can go beyond Hartree Fock later, but the determinantal picture will keep in mind for all many electron problems. And this is important for whenever I go to many electron problems. I think probably have time to stop. Yeah, so I think we'll stop here today. And I will actually look at the 2 electron problem, which is excited state. That is very interesting. Not only in terms of how do you construct, but how do you construct the spin adapted state, singlet and triplet. Because for example, I have 1s1, 2s1. It's an excited state of a helium atom. So there are lots of possibilities here. Alpha, beta can be anywhere. So what happens to those determinants? How can you spin adapt them, first of all? We all know that if I have 1s1, 2s1, you can form singlet and triplet. Alright, so I'm going to come back to this problem. What are singlet, what are triplets? Through this Slater determinant picture. If I have 1s square, If I have 1s square, I didn't want to mention, but 1s square is necessarily a singlet string. S equal to 0, ms equal to 0. That is very easy to see because you have just 2 electrons, one in alpha, one in beta. Alright? But moment I do excited state, it can be either alpha alpha, alpha beta, beta alpha, beta beta, all. There are 4 states obviously. And how do they break up into what is singlet, what is triplet? Of course, right away you can see that triplet has 3, singlet has 1, so those 4 states are singlet plus triplet. But what are triplet, what are singlet? I want to write down the determinants. I think for students it is very important to write down the triplet determinants. And they are not very simple. Okay, so you will see that. So we will come back to this problem of excited state of helium. Again, simple single determinant before I talk of electron-electron interaction in a more complex way, the correlation problem and so on. Before that, I just want to mention what the part that I am going to teach. I am going to bring in after this, how do you get this single determinant, that is the Hartree form, very quickly. It's a small review. And then how do we go beyond Hartree form for electron correlation? That is where I have to tell a very interesting problems of Coulomb hole and Fermi hole, and how that physics can be translated into developing or devising wave functions which go beyond single determinant. I think that will be very important, like perturbation theory, CI, cluster expansion, several methods are there. And then I'm going to mention towards the last part DFT. In fact, the reason I said DFT is quite different because DFT will be probably already talked in solid state a lot, but I'm covering DFT a little bit later. I want to mention that in spirit DFT is very different. Because in DFT, we never solve A psi equal to E psi. I first want to mention that. We never explicitly solve A psi equal to E psi. Explicitly. There will be an underlying psi, but we never actually solve A psi equal to E psi. So that is the reason I will bring in DFT a little bit later. So what is the spirit of DFT? Because DFT is something that the physicists use a lot, but actually DFT is not solution of the Schrodinger equation. Explicitly. It only says that the ground state energy can be written in terms of density. But it doesn't tell you how do you solve A psi. It tells you how do you write that energy as a function of density. So it has a very different spirit. How do I combine these? So that is where there is a very important theory called density matrix theory. So you can understand the density matrix theory, which is basically wave function derived. DFT is not density matrix theory. But what approximation of density matrix theory will lead to DFT, which can still be potentially exact. I think DFT is a little bit more complicated, and understanding DFT is much more difficult, I can tell you. Understanding this is much easier, because you have a structure and you know how to improve. In DFT it is difficult, and the underlying wave function in DFT is always a single determinant. That is what is more confusing. Because I will be first telling you the single determinant is not exact.